Okay, first of all, thank you very much for inviting me here and for being here to listen to this talk. I will talk about spin pumping and probe in a system consisting of permalloy dots and topological insulator. So these are my co-authors. The work was done in Moscow, in Prokhorov General Physics Institute, and in MIPT. FISTEC, and the collaborators were 3 universities in Taiwan. They helped us a lot with experiment and with samples fabrication. So here's the outlook of my talk. First, I will talk about the motivation of this research and how it could be interesting for this community. Then I will talk about spin pumping experiment on magnetic nanodots, permalloy nanodots, and about simulation of this case. Then I will talk about spin pumping from Vortex, and after that I will come to the conclusion. So motivation. We know the, let's say, paradigm of the STT Spintronics it is based on combination of 2 effects. You pump magnetization with STT, spin transfer torque. You excite the magnetization dynamics, and then you probe it. You sense it by means of magnetic resistance. And technology gradually passed from anisotropic magnetic resistance, known from the middle of the 19th century, through GN magnetic resistance, and now tunneling magnetic resistance is widely used. And so all the STT spintronic is based on the combination of these 2 effects. So you create magnetization dynamics, and then you probe it with magnetic resistance, and you get the electrically measurable signal. Okay, and STT Spintronics is not limited by just memory, that we heard a lot of talks on that. There are a big family of devices beside memory. There is a microwave generator and microwave detector. There are memristor devices. There are stochastic devices which are used for cryptography, for example. So there is a big family of devices. And all of them are based on this paradigm, this combination of these 2 effects. And this is just some funny numbers from the industry. We heard the nice talk by Professor Denis that information storage industry made very huge progress, and the increase of the areal density of the hard disk is 1 billion times in 60 years. So this is the first hard disks. And mainly this progress was done thanks to the development of magnetic resistance. So we know about magnetic resistance. We know that the principle of this effect, that the electrical resistance in the system composed by 2 ferromagnets divided by the electric layer is resistance depends on the mutual orientation of magnetization in ferromagnetic layers. And in the first experiments, the system was pretty simple, and after that, let's say this technology made huge progress again. So it was initially the amplitude of the effect was 10%, let's say, and now it reaches hundreds of percent. But as a consequence, the structure of the stack becomes very complicated. So it is not this simple as it's shown here anymore. Now this text used in experiments and in technology is very complicated. And coming to the topic of, let's say, of our meeting, if we want to use this effect to probe the magnetization excited by optics, it will add an additional. It will make the stacks even more complicated than we see here. So can we use? Can there be any alternative for that? Can we use any other effect instead of tunneling magnetic resistance? And a possibility is to use inverse spin Hall effect as a probe of the magnetization dynamics. So this is the principle of inverse spin Hall effect. There are there is a ferromagnetic materials attached to non-magnetic, let's say heavy metal or other non-magnetic material, and magnetization is excited by external means, and spin pumping occurs, and it creates voltage at this metallic layer. And in spintronics, as is in STT Spintronics, we use spin polarized current to excite magnetization. Here we can use external stimuli to create magnetization dynamics, for example, optical excitation, and it should be detected somehow, and possibly inverse spin Hall effect can be used. And so in our research, we aim to answer two questions. First question is what is a good material for that, to use it as the sensing layer, and what is the effect of nanostructuring. So about the material, there are a lot of evidence that topological insulators like bismuth selenide could be very good candidate for this purpose, because they demonstrate very high efficiency of spin orbit torques. This is a kind of there is a nice article on that, and it is demonstrated that topological insulator could demonstrate the best spin orbit torque efficiency and consequently the lowest power consumption. And the second question is nanostructuring. So if we use this, if we use these materials, what will happen if we nanostructure the devices? So if we use not the continuous layer, but the small let's say realistic geometry, and so all the real spintronic devices are nanostructured, as we know, and but nanostructures can cause some new phenomena, some new effect in magnetization, like that can occur at nanostructured system, like nonlinear synchronization, collective dynamics, sophisticated magnetization distributions like vortices and skyrmions, domain walls, and some other particular dynamical effect. And so in our research, we aim to address these two questions, two issues. And for that, in Taiwan, we fabricated such samples. So they were three series of samples with different sizes of nanodots made by permalloy, deposited on topological insulator. And to compare, we use this sheet film of permalloy. So just bilayer permalloy topological insulator. And then we studied this system through ferromagnetic resonance technique with this spin pumping. So for that, we put these samples into ferromagnetic resonance conditions, and we measured the output voltage coming through the inverse spin Hall effect. So these are the parameters of the experiment. This is the constant field. So it will change through the experiment. And this is the oscillating orthogonal field to the first one. So this is the result of the experiment. You have we see two spectra. This is the voltage one, and here for the continuous film, it shows the classical behavior. And for nanostructured device, we clearly see two peaks. And even on the voltage signal, we see these two peaks. And the idea was to understand what is the origin, what is the nature of this high frequency dynamics in these peaks. And in the literature, we saw that in a similar system, nanodots with similar, let's say, geometry, such peaks were already observed. This was the edge mode. So in addition to the ferromagnetic mode, the edge mode was localized on the edge of the disk. And the idea was to analyze this effect. And for that, we performed the micromagnetic simulation on a single disk. So we reproduced the condition of FMR experiment. So we applied again In simulation, we applied two orthogonal fields, continuous and oscillating one. And in fact, we observed this high frequency edge mode in addition to the Kittel mode. And to analyze the, let's say, localization of this mode, we split it numerically the volume of the disk into part, one in the center and another one in the volume. And we saw that this high frequency mode, in fact, is localized near the edges of the disk. So let's say what answer we can get from this result is that we observe this particular dynamics of magnetization, high frequency dynamics, and we can observe it through inverse pinhole effect through measurable electric signals. So it's a good way to probe. So we went further. We wanted to come to in our theoretical modeling to the electrical signal, and for that we consider, let's say, inverse task. So we calculated the spin current coming from the spin pumping, and we calculated the charge current, which corresponds to this spin current. So we use the model previously developed by other groups. So we use this model developed by Tserkovniak and colleagues and Chen and Zhang. So we calculated the spin current using the data obtained from the micromagnetic modeling. And then we estimated effective damping constant, which consists of the intrinsic Gilbert damping plus some additional damping caused by spin pumping. So there is another channel of energy dissipation. And using this data, we calculated the charge current coming from inverse spin Hall effect, coming from the inverse spin Hall effect, using the data of real micromagnetic simulations. And here is the then we simulated the voltage that could be expected using this data from the array of the dots. And here are the results, which are, let's say, very comparable to the results observed in the experiment. And using this data, we estimated the value of spin Hall angle, and the results you can see here. And you can see that it's the nanostructuring effects on that, but not that strongly that it could be. And what we and this is the final voltage signal. So what is the conclusion of this part of the research? That this method, inverse pinhole method, can be sensitive enough to probe very teeny magnetization high frequency dynamics. And we wanted to analyze another case of magnetization high frequency dynamics, and for that our second case was to simulate the spin pumping from the vortex, from the gyrotropic dynamics of the vortex. I remind you in few words what magnetic vortices are. So this is the, let's say, magnetization distribution, which is described by curling magnetization in the whole volume of the disk, and only in the center magnetization goes perpendicular to the plane because of the strong exchange interaction. So exchange interaction pushes magnetization out of the plane. And this distribution corresponds to the energy minimum to the big set of the geometries. So it's a natural magnetization distribution for the big set of geometries of the NAND disk. So it forms naturally. the interesting feature of magnetic vortices that under the influence of spin polarized current or other external stimulus like oscillating magnetic fields, the vortex start to gyrate with gyrotropic frequencies. There were big set of works on that. So if we see the let's say the dynamical behavior of the vortex as a function of amplitude of the applied spin current, which excites the vortex gyration, we can see this nice behavior that frequency linearly depends on the amplitude of the external current, which excites the vortex motion. In our simulation, we consider also the vortex excited by external voltage, and the idea was to simulate to understand the voltage, inverse pinhole voltage coming from this effect. And so we applied here an external magnetic field to break the symmetry, to shift the core of the vortex from the geometrical center of the disk. We performed the micromagnetic simulations, and then we calculated the distribution of generated spin current averaged over the period of the rotation of the disk. Here it is. And the corresponding inverse pinhole generated charge current density. And then through solving the spin diffusion equation, we simulated the electrical signal on the adjusted topological insulator. And what we see is that this signal is measurable actually. So this work is still in progress, but let's say tens of nanovolt can be expected from a single nanodisk, which is pretty measurable. And again, what we show here is that inverse pinhole, this electrical technique, is a good way to probe the magnetization dynamics. So we come to the conclusions of the talk. So we consider the two cases of magnetization dynamics analysis through inverse pinhole effect combined with topological insulator as a sensing layer. And we analyze these cases both experimentally and theoretically. And our results suggest that inverse pinhole effect probing through topological insulator sensing layer is a prospective tool to electrically detect the fast magnetization dynamics. And of course, the idea, let's say the future work would be to extend this method for ultra-fast magnetization dynamics. Okay, thank you.